Okay, so today I want to talk about what does it take to design a product. And why am I talking about this? I'm talking about this because of for my final year in university, I had to design a bicycle along with my team, a folding bicycle. And we wrote a report, made a poster, and actually manufactured the bike. And in case someone's curious about how a manufacturing process looks like, what does it take to design a product and make a product, um, here's what it looks like. I'm gonna go over the report. I'm gonna go over the poster, what it actually turned out, the problems, and things to keep in mind. So this video will talk about firstly, what does an engineering report look like, which is useful to know. And useful to know because if you're ever gonna read engineering reports or studies or things like that, it's good to know what you're looking at. And second of all, what does it actually take to design a real functional product? So just showing, so here I should be showing a poster in the background. It's actually recording the screen, so we'll see how that works. But look at the poster we made. In the middle is the rendered image of our bike. Now that's the rendered image on the software we use. We used SolidWorks to render this image. So if I zoom in, let's see. So this is what it's meant to look like. And if we actually scroll down, let's see. So looking here is what it actually turned out to be. So we didn't get time to paint it, and we didn't get time to like tidy a few things up. Like for example, you can see the brakes are kind of like hanging there and stuff, and the seat is a bit higher than it should be. A few things like that, but it is a functional folding bike that we designed from scratch, just except for things like the wheels and pedals. Like the actual frame was designed and manufactured wholly by us. So here's what it looks like when it's folded. That box is the size of like a medium-sized suitcase, maybe a large-sized suitcase. Now, we did make a few mistakes, and it doesn't actually fit into the box perfectly. We'll go over that. I'll go over that towards the end, But let's just say there's a prototype and not the final iteration. And throughout this, there's some of the things we did throughout the designing process. Now, this poster, it's submitted now. It's from our uni, of course. So I just looking back at it, there's a few things with it that aren't perfect. Like there's a lot of white space here, and the number in here doesn't match the actual bike. So and also like this kind of looks like there could be one more of these here. I had to crop our names out and stuff from the top, so that's why it is not, a few things missing. But oh no, sorry, I guess the numbers are here. Oh, okay, it's not too bad then. It's not too bad. Okay, yeah. And by the way, I'll show you the report now. So going back to the report. Okay, let's see. So one of the things is that with the report, you're doing you're going to be doing about 10 times more work than there is in the report. So if the report's 40 pages, you're doing 400 pages of work. With your research, market research, reading is going to be even more than that. Like you're going to be doing lots more work, and it's going to be all summarized. And that's why you have to have lots of references. So just starting to start. I had to take out some names, although now you see my uni, which I don't think it matters. Sorry about that. So this is a university report. So it's going to be slightly different than a report you would see online or the studies you would see online. Basically this, I don't think you would ever see this in a real report in industry, as far as I'm aware. But just looking at it, it's basically a title page. We had a supervisor, our doctor, who was a manufacturing and mechanics specialist, our names, our ID, and then what we did. But that's not true. We all did everything, because you can't just have one person do one thing. Everyone did everything, but you had to mention this. Now, the summary is the first real part of any report. It basically, as my supervisor described it, if you look at if someone's looking at this report, they see the summary, and that's what they decide on if they want to read the report or not. So, what it has to contain is, reading from my notes here. So it has to contain the objective of your report. So our objective was to design a bike. Second of all, what do we do to achieve this objective? So we want to design a bike within some constraints. How do we ensure those constraints are met? And third of all, well, thirdly, I don't know, the outcomes of the investigation. So the final product, the bike, the poster, what I just showed you there. This summary is a bit longer than it should be. It's about, if I remember, it's like 300, 400 words. It should be up to about 200. This is a bit too long, but it's okay. So if you're doing a summary yourself, I would keep about this much. The objective, the process, the outcome. Lots of this information is unnecessary. Make sure to include references. Make sure to reference your references properly. But I'm assuming you know how to do that, or just use the internet. Also, a summary. When my other supervisors mentioned, you should keep it interesting, make the reader interested. Or sorry, oh, that actually maybe for the introduction. Scrap that. Contents page. Well, content. That's easy as well. I'll just go through it as we go through it. Nomenclature. It's pretty self-explanatory as well. Just what symbols you used and then explaining them. Abbreviations, also pretty self-explanatory. Just some people believe that even if you mention PDS in abbreviations, the first time you mention it in a report also include what it means. So you'd have PDS, product design specification here, and then later on have it again the first time you mention it, just to make it clear to the person reading it, so you don't have to always go back. But that's like a very specific thing. So introduction, yeah, sorry, this is what my other supervisor mentioned about making it interesting. So the summary should just be quick, to the point. What objective, procedure, result. Then introduction, you could make it a bit more fluffy. You could make it a bit more interesting, set a scenario, a bit of history lesson, like here we went with history and such. Also mention what our actual goal is. So massive, less than 10 kg when folded, should be capable of fitting inside a suitcase of approximate dimensions, yay big. I hope this is recording. I'm trying to record this. I hope it's recording. Like the screen. Let's see. Also, we picture here. I would recommend. So one thing is about images and reports, engineering reports, is. So this is just like a logo of our imaginary company that we had for like a case study. Engineers like their reports pretty much straight to the point, technical, no waffle, no fancy language. Keep it simple and don't add stuff that shouldn't be there. Like my professors and doctors, supervisors hate like fluffy language. So also, and that would also mean fluffy images. So I'll go over that as we meet it. Market analysis. I actually did there was a section I was in charge in. So let's see. Was also one of the least interesting sections. Effectively, so once you have your report, summary, introduction, pretty simple. Just do what you want to do. Find out what you need to do. Market analysis. Okay, so we're making a bike, and why do you need to make a bike? So I think to keep in mind of market analysis is start with a big picture and then be a bit more specific as you go on. And also don't come in with some preconceived notions of who the actual market is. And keep an open mind and present that you keep an open mind. Don't just say, okay, I'm gonna give it to these people in this country for this price. Like, keep an open mind because you might find things that are unique. Um, so as you can see, as what I just said, starting off with global folding bike market, market trends and target audience. Um, there you go, figures, graphs, lots and lots of references. So this like is basically one reference per sentence because it's all statistics. Brand analysis. This is all just what customers consider important. Aesthetic analysis, financial analysis. Now, these two aren't that important, especially for an engineering report. It depends what your background is. If you're like a product designer, this is going to be more important. For an engineer, this is less important. The financial analysis, now this is more important again. So effectively, we find folding bikes, the price, dimensions, volume, weight, and what our goal is. You want to have bikes to, or a product to compare your product to, and in fact, some companies, if they're making a bike, they're gonna buy the best bike on the market. They're gonna take it to their workshop, strip it, test it, find out all the parts, their weight, their strength, everything, and then work like reverse engineer from that bike. So, but also with your own improvements, of course. But you work away from what is found to be working. So that's good. So make sure to compare to the market leader, which in this case is Brompton. So Brompton bikes, if you don't know Brompton bikes, they are really good, really, really good. They're basically perfect bikes, so it's kind of hard to compete with bikes that are perfect. I guess we compete with the price, and it is technically it's actually not smaller. Also because the decimal here is confusing. It's just the only thing you compete with Brompton on is the price. Like, you're gonna struggle to have a bike that's lighter, unless you do some fancy trickery. But Brompton's top of the line. Anyway, moving on. Material research. So for a bike, it's going to be aluminium or steel, and then titanium, carbon fiber. You want to mention everything. So we had a budget of £500, and it will be sold at 800. Now that means we're not going to be using carbon fiber. Also, we don't know how to work with carbon fiber. But at this stage in the report, you have to, and at this stage of designing, you have to keep an open mind that what actually is the best. So I think here we found that Kevlar fiber reinforced polymer is the optimal material, and that was based on tensile strength, yield strength, Young's modulus, toughness, density, and such. Yeah, it is the best, but we can't work with it. We don't have the resources. We don't have the machines to work with it. But you have to know what is the best and and also why it's the best. So by the way, in a report, you can't state anything. So we originally stated that KFRP is the best material, most optimal material, but our supervisor said, okay, it is based on what? So that's why we added this part. So you can't state anything. Even with a reference, you kind of want to state the factors within the reference. So that's what I mean. Engineers hate fluffy language, but they equally hate lack of detail. So keep that in mind. So effectively we said, yeah, aluminium's more than likely the best. Well, actually we kind of knew aluminium's the best because we spoke to the technicians in our store, which is another good resource. If you're designing something, speak to the people, not just the designers, but the technicians, the welders, the machinists, fabricators, because they will tell you the real, like, a designer might say that Kevlar fiber reinforced polymer is the best. A technician will tell you, we're not gonna work with that, and we don't like steel, use aluminium. And then if you piss off the technician, you're in for a bad day. You work with your technician, ask them for help, and they probably know more about like what's possible, how to do things than a designer. keep that in mind. UK Folding bike trends, more market research, Fury. See, basically all of this is almost useless. Almost useless. What do you mean by that? From an engineering point of view, that is almost a waste of time because we don't want to be doing. So moving on to report like a wee sneak peek. We're doing some calculations. We're doing some, even more so, actually designing the bike, testing the ideas, prototyping. This is what we want to be doing. See all of this? This is what we have to do. So basically, also in the engineering report, my supervisor said, we don't really care about your market research unless it's really bad, really good, because everyone does that. But it's really out there. But we want to see what you made, what unique design you have. All of this, it's already out there, but we're making something new. That bike's no one done the bike before, and our folding mechanism is unique. So that's what's cool in the report. So keep in mind that don't talk about things that aren't important. What you make is the important part. So let's see, moving on. Material selection. So this is the way that materials are selected for a product. In case you don't know how this works, you effectively have, if I just zoom in, let's see. So here's a package that we used, and you just think about, okay, so I have a bike and I want to limit stiffness, optimize mass. So what does this mean? You want it to be as strong as possible and as light as possible. Look in here, and you will see, like here, let's see, here someone's heavy and weak, and here someone that's light and strong. So you get like a range of, you get the range and a visualization of the materials that are actually useful for you. So let's see. So I think basically everything over this line, to the left of this line, is a suitable material. Everything to the right is not suitable. So going here, we did something similar, but with cost instead of mass. And you can see that aluminium is in both, and steel is in both. And the likes of carbon fiber and titanium are only in the first one. So what does this tell you? Steel or aluminium, simple as. Bike frame analysis. This is probably one of the weaker parts of our report. And why is that? That's because, no, I can't tell you. We did a basic mechanic, like frame analysis, as it says, to see, an objective of this was, if we scroll down, we want to work out the stiffness to mass ratio, because that's an important factor when designing like a frame or a bicycle, things like that. And we found that aluminium is slightly better in this regard, and that we went with aluminium for our final frame. And I think there's also here someone else did this, so I'm a bit less knowledgeable. Looking at this, I'll be honest with you, I'm not actually sure how this works. I have to read about it. Yeah, I'm not quite sure what's going on here. I'm gonna have to write about this for my interview. The result is, though, aluminium has a better stiffness to mass ratio. That's why we went with it. Let's see. Also, stiffness to mass ratio, keep that in mind when designing whatever you're designing. So deciding on the size of the tube available, we kind of got the sizes that are in the store, so we knew what we were working with, so we had limitations. But we also had this resource. I found this really good website, but I can't remember. I couldn't find it again. It was a website that showed you if certain parts of a bike are oversized or undersized for the stresses they experience. So, for example, the front of the bike, the part that the steering wheel's on, that we do, is tends to be oversized, but it's oversized because it has to fit the bearings of the steering wheel, which is like why it's oversized, but still is oversized. But based on that and like average sizes of parts and the available materials in our store, we came out to what we're working with. So we want to, these are all the parts or the main parts in the bike. And here's the alloy and size we used. So we used aluminium alloy 6082 with these sizes based on what we have in the store. And yeah, we also made the assumption that 60% of the rider's weight is going to be on the seat and 40% on the handlebars, which is a pretty, as we have, it's a reference, so it's a pretty standard assumption. Okay, let's see. Gear ratio analysis. Oh, this video 22 minutes long, and I'm only partway through it. Okay, I'm gonna have to skip through some of this stuff. 22 minutes long, that's so long. Okay, let me take a drink of water. It's getting so long. Okay, so let's start skipping through things because, yeah, I think I'm being a bit too specific to the bike. Yeah, basically all of this, what I probably should have said, this is all theory to relevant to your project. Find out what your theory is and do it. Design process, what's your project plan? Not that important. Product design specification, this is important, and I'm actually need to pick up on this. I'm not that knowledgeable about it. As far as I understand, we should have a snippet of what it looks like. Yeah. This is very, if you're designing anything, use a PDS, and anyone who reads about what you did is going to love you. You effectively pick performance factors, and like based on your specification, what it needs to be, design intent, reasons for. You can copy this structure for it, but make sure to include the PDS. As you can see, our weight size is specified, so we have to keep within those specified values. Let's see. Design concepts. Yeah, I'm gonna have to read on this as well. Not knowledgeable. Let's see. Oh, here's a good point. See words like BSEN, whatever. Those are like official international standards of bicycles for safety or whatever else. Make sure to include international standards as part of your referencing. Okay, now here we're getting to interesting stuff. Design concepts. So effectively what happened was what happened was there was like 6 people in a group, and we were all given the task of, like, we give ourselves a task of come back with 2 designs for a folding bike in the next couple of days. And here you can see some of the most popular designs we had by the way they fold. So here it folds in half, and then the wheels meet, which is pretty simple. Here this is actually my design. This is one of the designs I came up, swivel fold. And kind of like the seat turns, and it and that like the wheel meets the rear wheel meets the front wheel, and the handlebar like folds as well, kind of, and you take the front wheel off, which is pretty cool. It's pretty good we didn't go with it because it's pretty complicated, but and here's the design we actually ended up going for. Basically it's pretty weird. I'm pretty sure it's actually a unique design that no one has actually done this before. Like the seat comes up, and it connects to lats that you can undo. Then the real wheel comes around to the front wheel, and you can then collapse the steering wheel and the seat as well. But like that latching system is unique, which is what you want to be doing. Concept convergence. Okay, so we have 3 concepts, and which one's the best? So first of all, in engineering, in the real world, you can't just say which one you prefer. Yeah, you can't just vote for it. Which one do you like the most? You need to have a methodical, oh, a real system to analyze which uh designs the best. Look up concept convergence and the Pew matrix. It effectively is like a point system that you give to each criteria, and then you can rank the bikes or the concepts based on those criteria of a certain weight, depending on which one's the most important. Nah, it's okay. Um, uh, yeah, it's okay. Just the names were there, but I don't think it matters. There's no surname or nothing, so it should be okay. Anyway, where am I? Da, 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 da. Yeah, this is how we actually pick which design's the best, and it came up to being that the last one I showed there. You make a prototype, a soft prototype. So here we made it from laser cut wood that we glued together and shaped in. And this is just thermal, some sort of plastic tube, but here it's a 3D printed part. So it's kind of like it looks good to say laser cut and 3D printed. So make sure to make at least one soft prototype. Here we made like two for the two parts we're going to use. This is very important. Design DFMEA, design failure modes and effects analysis. Damn, I don't even know what this means. Let's see. So scrolling down. Where is this? This is another like manufacturing type process to judge your bike on. So effectively it's like make sure that instead of guessing things, to find real methods to analyze certain problems. So as far as I can read here, the effects after a few hours. As far as I understand, it's like predicting risk. So that's that. Make sure to use a specific one for what you're doing. Let's see. So this is a sample from the DFMEA we did. Right, for just one part. So this is one part, and like these are all the requirements of it. Here's what we came up with. DFA, design for assembly. Like, see, you basically you can tell which parts I did based on how much I know about them. We used a Lucas Hall. Sorry, someone in my group did it. I didn't do it. The Lucas Hall DFA to determine how the bike design would be suited for being mass produced. So, if you're designing something, it's gonna be made. It's gonna be mass produced, and there's a method of simplifying or judging how efficient that process is. So, this is basically one idea we got is make sure that the things you do can't be done by anyone. What does that mean? As engineers, we have certain skills and knowledge that we have to apply in our projects. We can't just, because any person could design a bike. If you could design a bike, but could you apply the DFA method? Could you apply the DFMEA method? Could you actually design the bike in, special software? You have to use your specific skills from your education and expertise in your projects. So moving on, now this is the part I know a bit about, because this is the part I did. Finally, the part I did. Finite element analysis. Quite a lot to be said about it. So first of all, as you see, here we have a bike, a folding bike that already exists. We tested it for strain and stress within it to know what we're working with. If our bike that we design has comparable strength to a real bike that already exists, then we know that the bike is pretty strong because it matches what already exists. So that's what I mean. If you're making a chair, find out how strong a chair is and make sure your chair is as strong as a normal one. Simple as. Moving on. Oh, assumptions. Yeah, basically, if you're designing anything in software, it's going to be simplified because real life is infinitely complex. So you have to simplify it to make it possible to be analyzed. So we used two software for analysis, SolidWorks and Abacus. Abacus is awful to use. It's a hateful software, but it's good, but it's hard. SolidWorks is easy and it's just about as good. So we use mostly SolidWorks, but you should use effectively. Your design has to be verified, and you can't verify something on one parameter. So here you can see that you verified our displacement on experimental results, SolidWorks results, and Abacus results. If you verify it on one thing, it's not verification, it's guessing. So based on this, we knew that. And what's the purpose of verifying your software? When you make a design in software, as I mentioned, there's going to be assumptions, and you have to make sure that those assumptions are valid, that they're not like too crazy. If your experimental results and your design results are comparable, it means your assumptions are valid. Simple as. Moving on, let's see. Analysis prototype. So here, there's quite a bit of text. Like this is actually the part I did. Like basically all of this here is my own work. So I effectively find a report that had force conditions on certain loading events. So if a bike goes over a bump, how much force is going to be experienced? If someone's riding a bike uphill, how much force is it? I find those values, I input them to the software, and it gave me results for stress and displacement. The thing is, you want to be doing, if you're designing something like this, make sure to give a good detail to what it is. All of this here is basically what is the mess, what is the design inside of made up of. So someone reading this with technical knowledge can be like, yeah, this makes sense, or this is not accurate. This is what I want to do. You want to give the background to it. So it did all of these loading events, and you can see the force distribution with it. Like basically where it's like colored, it's where there's more stress. And I effectively found that there's 3 parts in the bike that are experiencing the most stress. And there's one part, the wee lats that I mentioned here, that is experiencing the most stress in like every condition. So it has to be reinforced, was one of the improvements we made. Here, bit of lag. Here, this is, let's say, in case you're not an engineer, let's say you have a part, where am I? What would be a good example? Like if you have like tweezers or something, tweezers for your eyebrows, whatever you call them, or anything. If you have a car or something, or like a pencil, it's like if you apply a force to it, it might be able to resist the force. But if you apply the force 1,000,000 times, even though it's the same force, it might fail after repeated loading. This here is the total life cycles of this part of the bike, one of the latches that's not shown here, part of for the fold mechanism, how many cycles of use it can survive based on the loading condition stress. More background for information for you. You basically assume if the bike's going to be used for 5 days a week, 2 journeys, it has to survive 4,800 cycles. And here it says it's going to survive 6,000, so it passes. And here this is the miner's rule that is also part of the static loading case cycle life. Intellectual property, you want to make sure that your bike is not infringing on someone else's design. There was a similar design made once by someone, but it's still it's pretty different from what we made. So we could make like a patent for design if we wanted to. So that's our option. Here's more systems are kind of similar. You just have to, because you have to make sure that your bike or your design is not infringing on someone else's existing design. Costing for a prototype and such. If you're making something, it's going to cost. Simple as. So account for that. Business expansion. Yeah, this is just like more manufacturing stuff. Final prototype. Like now we're getting to business. Now we're sucking diesel. Let's see. So here's what our bike should look like. Here's what it look like. It's pretty similar. It's pretty good. No color because just run out of time. But like I said, from that, it looks pretty similar to what it should look like. But big problem, it doesn't fit inside the suitcase. Why it does not fit inside the suitcase? Now, when I know exactly why. I know exactly why. It's because when we were designing the bike, someone made a problem when they were doing it in the software. Of course, here's a front wheel, here's a back wheel, and they should be aligned. And then it should fold like this, so it folds like beside it. But there was a problem with folding it in the software. Like it wasn't gonna fold. It was a big problem. What happened was someone tilted this, sorry, like this, so it would fold more evenly. But because it was folded, then it was actually made. It messed up the angles. It messed up the angles. Because someone just wasn't sure how to fold it, and then they angled it, and it messed up, and then that's why it's sticking out so much instead of being flush with it. Uh, hey, it's a problem here. We can solve it in the future, but that's how it was made. It's still a prototype. Yeah, so it's the MB1 prototype. So it doesn't have to be perfect the first time, but it's a damn stupid mistake. But here, if it was perfect the first time, that's not it means you didn't do anything good. Like if you make something and it works the first time, you made something that's boring because it's too simple. It did meet the weight requirement, and it folded within 27 seconds. 30 seconds was our goal. So it's okay. It just doesn't fit, which is annoying. Also, the seat is a bit too high, as far as I remember. The pedal angle is a bit small. Like, just looking at this, what I would like to do is see just the improvements of it. See the way that the rear wheel connects here. Most bikes connect it behind it, so this should be connected behind it. This should be a straight line up here, so it's not sticking out so much. This could be a bit higher, like here, so you have, and the pedals could be a bit longer, so you can cycle a bit better. This was just designed a bit pearly, but it's still adjustable, but not as like this pipe here should be shorter, and the pipe that goes inside it should be able to be adjusted more. When it's folded, this is at an angle. I think there's an improvement we mentioned for it, but let's see the improvements. Discussing improvements. Let's see. Yeah. Basically sorted by breadth. I'm actually not sure what whoever wrote that what it meant, but like it has to fold better. We skipped the final prototype. So once you make your product, whatever it is, take pictures of it, write about it, test it. Test it's a big thing. So test weight, size, folding time, ease of use, and just test everything for yourself. Discussion. Let's see. Just skipping here. Let me just take a look at my notes. Yeah, okay, so discussion is going to be the creative part. So everything before it is technical, especially like the testing is all technical, design's all technical. But discussing can be a bit more creative, like talking about how it can be used, the good things you did, the bad things you did, what you learned during it, during your project. Just discussing improvements, improvements. What did you mess up? How do you unmess it up? Conclusions. Um, it's a concise summary of what you find. References. So here I'm gonna go for the references in case anyone wants to look at them. Yeah, basically have like a reference a page at least, more or less, more or less. And here's our full DFMEA we have. I think this is DFA and market research. You know, a lot of stuff you do will not be included in a report because it's too long. Simple, like, you know, can't have everything. So effectively, this video is 40 minutes long. Oh, that's so long. My throat is sore from talking. But in summary, keep the boring stuff in the start of the report to a minimum. Get to the meat and bones of it, with what you actually did. Take a risk and do something unique, and be technical, be specific. Don't ramble on like me for this video. 40 minutes long. God, that's awful. Well, I think I covered everything to some extent. I actually did this video because I have an interview on a project in a week, next Wednesday. So I wanted to do this to like prepare for it, to talk about it. And I kind of know which parts I know nothing about, so that's it. Well, thanks for the video. Thanks for listening. See ya.